So welcome everyone to this afternoon session. And it's a great pleasure for me to introduce the speaker, Daniel Figueroa. So Danny is professor in Valencia, and Danny has done a lot of work on gravitational waves. And before that, a lot of work on preheating after inflation. So that's a connection with Will Kinney's lectures. And so thanks for accepting our invitation to speak, and take it away.
Okay, thank you very much, really, guys, for the invitation. It's a great pleasure to be here with you guys, even though it's only virtually online. It's too bad that the pandemic carries on, no? Because I was really looking so much forward to go to Bangalore, okay? So anyways, we'll do the best we can, which is online lectures. And I'm gonna try to make them a little bit interactive, which is difficult, of course, because students are probably mute. So let's say that in some moments I may ask some questions to the audience. And in those moments, I'll be happy if the people who have control over unmuting the students can let them ask the question, okay? Or they can write it in the chat.
This is Sriram. I have the control. So they just need to raise their hand and I will unmute them.
Excellent, excellent. Thank you very much. Okay, so let us start with the lectures. The title of my lectures is going to be something like Cosmological Backgrounds of Gravitational Waves. As Robert said, I'm based in Valencia, in Spain, in the Mediterranean coast. So you are all very most welcome to come visiting. Okay, it's a beautiful place. It's a sunny place, as you can tell. And I'll be very, very happy to host you at some point if you want to come visiting once the pandemic goes off. So I am responsible for giving you 3 lectures on the topic named here under the acronym GW. GW 1, 2, and 3, today, tomorrow, and on Friday. GW, of course, stands for gravitational waves. More concretely, the topic of the lectures the organizers asked me to give, it's something like generation and imprints of primordial gravitational waves. Okay, this was the more specific title. Let's zoom in into this name. And for the very observant people, they may have noticed already that somehow this doesn't fit exactly with the title I was putting in my cover page. No? Whereas I was writing Cosmological Backgrounds of Gravitational Waves, the original title given by the organizers was Generation and Imprints of Primordial Gravitational Waves. So the question is it the case that primordial is the same as cosmological? And it turns out that in practical sense, yes. So essentially, very often people refer to primordial backgrounds when they are talking about the background of gravitational waves from inflation, but that name was given like 30 or 40 years ago when there were no other backgrounds from the early universe. Since in the last 20 to 30 years, we have worked out a lot of other gravitational wave backgrounds from the early universe. I definitely prefer not to talk to them about primordial because I don't think they are more primordial than anything else, and rather simply as cosmological backgrounds. Okay, so essentially that's the first message. Cosmological backgrounds is the same as what some people refer to as primordial backgrounds, but I'm just gonna keep it simple and call them cosmological. GW, as I said, stands for gravitational waves, so stick that in your head because we're gonna use it everywhere. So once again, just before I move on, primordial really only implies cosmological backgrounds. More concretely, if you want, those coming from the early universe, and we will define in a moment what we really mean by early universe. And to make things more complicated, very often, because these backgrounds are stochastic, they are also called stochastic backgrounds. Okay, so in summary, either primordial, cosmological, or stochastic backgrounds means pretty much the same, has to do with backgrounds coming from the early universe. Okay, having clarified this, I think we can proceed with the lecture, with the first lecture on cosmological backgrounds of gravitational waves. And I'm going to start, of course, with a motivation. This is going to be a bias motivation because I'm a cosmologist. So I'm going to give you motivation based on the perspective of a cosmologist. Right. We are living, let's begin by stating that we are living very special times, okay? In the history of research and of physics, we are living times of celebration because we have finally detected directly gravitational waves successfully, okay? And this is a non-trivial achievement, really non-trivial. This is a milestone in physics, both in theoretical physics and in astronomy. It has taken us 100 years, okay? So you should really realize how relevant it is, this moment in history, because the prediction of the existence of gravitational waves was really made a century ago. And it has taken us literally over 100 years to start making detections. So this is a special time because through these detections, we are making fantastic discoveries. We are measuring, discovering, if you want, that there are plenty of order 10 solar mass black holes in the universe. We can, of course, through the detection of the signals emitted by pairs of these black holes or black hole neutron stars combinations, we can test the paradigm of black holes themselves, and also the physics of neutron stars. We can further test the underlying theory of gravity, general relativity, and look for deviation from it, and so far no deviation whatsoever. And in general, let's say what these observations give us is the new perspective to observe the universe through gravitational waves. It's a new way of observing the universe. All these first points are extremely interesting, and it's what's happening now, really now, in the last 5 years, and it's gonna be happening in the next years, shaping the paradigm of what we can do with gravitational waves from these kind of binary objects. This is very interesting, but we are going to focus on something else. Okay, stay tuned, of course, because as I said, there's a lot of fun and interest in following the coming years, no, in the discovery and search for gravitational wave signals from binaries. But we are gonna rather focus on something else, which is this particular aspect. We can observe the universe through gravitational waves, which is the same as saying we can observe the universe through a new pair of eyes. Okay? It's like when people invented the microscope. You could not see the reality at the microscopic world until you use the microscope and discover that there is a whole world by itself living at the microscopic scales. No? So this is the same. Now we're going to discover whatever is the gravitational sector of the universe that gravitational waves allow us to see. Now, observing the universe, the whole universe of gravitational waves, what it really means is to do cosmology. So essentially what I want to do with gravitational waves is to do cosmology. Now, if we talk about cosmology, this implies that either we discuss late universe cosmology or early universe cosmology. And in both cases, we can do something with gravitational waves. In the first case, in the late universe study of the evolution of the universe, no, we can actually study standard sirens, distances in cosmology. In other words, we can measure the Hubble rate today, the question of a state of dark energy, also determine to some extent cosmological parameters, test modified gravity, do lensing, etc. A number of very, very interesting things. However, again, I'm going to focus instead of something else, which is the ability of using gravitational waves to probe the early universe. Why is that? Why are we interested in this? Because the early universe is characterized by high energy particle physics phenomena. And therefore, what we want to do here is to study, to learn to what extent we can study particle physics of the early universe using gravitational waves. In other words, I want to answer the following question. Can we really probe high energy physics using gravitational waves, say as we do with colliders nowadays? And if so, if we can probe high energy physics, how? Okay, so answering these two questions, these two fundamental questions, is at the core, at the heart of the lectures I'm going to deliver in these 3 days. All right, So gravitational waves as a proof of the early universe, as the high energy physics phenomena of the early universe. The first question is why? And this question is addressing all the students attending the online lecture or the lecture in person. So why? Let me give you a clue. There is one and only one reason. So any guess, somebody dares to answer why we can use gravitational waves, and what is the reason and only reason that gravitational waves allow us to prove the early universe?
Can you raise your hand, please, so that I can unmute you if you wish to speak?
Any guess? Whatever, guys. I don't see the list of people. Ah, yeah, a couple of hands. Oh, very good. Okay, let's hear one of the answers.
Yeah, unmute and speak, please. Suashish and Kinjal.
This is Kinjal. Just a wild guess. There is less dissipation, and these are tensor components.
Okay, that's one guess. Thank you. Thank you. Another one.
Ashish and Yashraj Singh.
Yes. So hello, Yash. This is Yashraj Singh. The one reason I can give, we can use gravitational wave because gravity is so weak. So gravitational wave instantly decoupled from other interaction of the plasma that was in the early universe. So we can extract information very easily than light.
Thank you very much. That's the correct answer. Nothing wrong about the other one. We can also use those properties, but the one and only reason why we can actually do cosmology with gravitational waves, we can explore the early universe, is thanks to the weakness of gravity, as the previous person was referring to. What is the advantage, as this person was referring to? The gravitational waves decouple immediately upon production, which means they will propagate freely through cosmic history. What is the disadvantage at the same time? That is super difficult to detect them. And this is why today we still haven't detected any of these backgrounds from the early universe. And since we have just only recently started detecting the signals from the binaries, nothing strange about this. We know the difficulty we are facing. Okay? But facing on the advantage, we just learned, no? Because of this weakness of gravity, a gravitational wave is an ideal proof of the early universe. Once they decouple, they will retain their background, the background of gravitational wave, the spectral shape of whatever spectrum they have. So if for a specific high energy physics processes, there are a specific gravitational wave background with specific signatures, if we were capable of detecting these backgrounds, we will be able to tell something about the physics responsible for this high energy physics phenomena. I hope you see the logic. So what processes in the early universe of high energy characterize the early universe precisely? Well, let me introduce you to the early universe, people, early universe, people. The early universe is nothing else but the very first second of the universe, of its entire cosmic evolution. Is typically divided, this first second, into a period of inflation that I believe Will Kinney is giving you quite a lot of information about. It's also characterized, it's followed by a reheating period that matches the end of inflation and the onset of the standard thermal era of the hot Big Bang framework, which probably Mashahide will tell you a little bit about, and also David Wants, I believe. So, of course, inflation is a hypothesis, okay? It's not like there's a definite proof. I'm just gonna assume this framework, okay? Just to clarify. Well, this very first second is really tiny early moment, the first second literally of the whole expansion history of the universe that so far we believe is of the order of 30,700 millions of years. But still we are only interested in this very first second because there's a lot of physics that is going to be very interesting for us. And this physics, of course, unavoidable, this physics I'm going to explain in the lecture, unavoidable overlaps with the content of some of the lectures by David, William, or Mashahide. but such is life. Okay, I'm going to try to focus on the particular aspect I want to cover here, but hopefully this overlap is just good, precisely because it will reinforce the ideas. So what kind of phenomena are we going to be looking for? Well, there's going to be fluctuations, quantum effects during inflation. There's going to be particle production during inflation or during reheating. There's going to be, we're going to consider possibility of phase transitions, either during reheating or during the thermal era, and we're going to consider the possibility that these phase transitions creates cosmic defects. Okay? All of these phenomena are actually very different among themselves. They don't need to have anything to do with each other. Well, in reality, cosmic defects are a consequence of phase transitions, but even that, not necessarily. But in any case, once you start describing them, these phenomena can be very different from each other, but they do have in common something very interesting for us. All of them emit gravitational waves in the form of a background. Okay, these are not single isolated events. It's a background of gravitational waves that comes from everywhere from these moments of the early universe. So the core of my lectures, again, it's going to be the study or the explanation of how we can use these backgrounds to prove the physics of the early universe, the physics that created them in first place. So the lectures are going to be covering first the inflationary period, then the reheating period, then we will enter into the realm of phase transitions, and then finally we will describe cosmic defects with a special focus on cosmic strength. There is a logic and chronological order naturally in these stages, because assuming inflationary paradigm, inflation takes place first, inflation is followed by reheating. Now, if there are phase transitions, they are either happen during reheating or afterwards. If cosmic defects are produced, they are typically a consequence of phase transition. So this naturally gives me a guideline, you know, an order in order to organize my lectures. So we are going to talk first about gravitational waves from inflation, then from preheating, reheating, then from phase transition, then from cosmic effects. However, you know, I could think of give you, 1 hour lecture of each of these topics, and then the remaining extra half an hour, well, we could have coffee, chat over the ideas, etc. But I think the lectures would not be complete if I don't include a pre-lecture, let's say, an initial lecture where we define properly gravitational waves. So I'm going to shift now the numbers of the topics, and I'm actually going to consider that today the whole lecture is going to be dedicated to the actual definition of gravitational waves. And the reason why we need a whole lecture is because defining gravitational waves is not easy at all. It's not straightforward, like electromagnetic waves in electromagnetism. Then we will do a second lecture tomorrow covering gravitational waves from both inflation and preheating. And finally, on Friday, we will cover the gravitational wave backgrounds from phase transitions and cosmic effects. So are we ready? I hope so. Let's start. Let me give you, in this lecture today, a primer on gravitational waves. Now, in order to talk about gravitational waves, we need to specify what is our gravitational framework. I'm going to stick to general relativity. I am not going to consider modified gravity scenarios. Those are very interesting. They have their own interest, their own possibilities. But since, let's say, so far, there is no specific observation that really strongly makes you think we would need to modify general relativity as the underlying theory for gravity, I'm going to stick to it. This is a field theory. This is a field theory that relates space-time geometry through this tensor with the content of matter through this other tensor, the energy momentum tensor. Okay, where the coupling constant is the reduced Planck mass given by this scale here. There, we're going to find elements such as the space-time invariant element, which essentially tell us that it is the difference between space and time intervals that is really conserved in this theory, and not separately the space or time intervals by themselves. And we are going to study in certain detail the depth of the symmetry underlying general relativity, which is the symmetry of diffeomorphisms, which is the symmetry that tells us that I can change arbitrarily from one system of coordinates to another with arbitrary change of coordinates, as long as it's a regular change of coordinates, and the physics of gravity should be absolutely the same. Now, in order to start describing gravitational waves, I'm going to dwell a bit more into general relativity, just in case there is somebody in the audience that is not so familiar with general relativity itself. Okay, so I'm going to do a parenthesis, like a break in our discussion of gravitational waves. First, I'm going to do a digression of what general relativity is, and I'm going to give you a mini primer on general relativity. So the equivalence principle. Let's start by the Gedanken experiment, the imaginary experiment in which an observer placed on the surface of Earth drops a basketball, and when she drops it, the ball accelerates downwards towards the ground and eventually hits the ground. No? And the acceleration, we know very well, is the acceleration imposed by Earth, gravitational effects on the surface. And now let's consider another situation where this person, or maybe the cousin of this person, it's inside a rocket that is moving with acceleration of intensity equal to the acceleration you feel on the surface of Earth. And as this rocket moves on, okay, moves upwards in this plot, this person drops the ball, okay, and what happens is that even though the ball doesn't really move, as we see by this straight line, dashed line, because the rocket is accelerating in the vertical direction here, what the person inside sees is that the ball goes down to the ground, to the bottom of the rocket, with the same acceleration that the person on the surface of Earth had experienced before. So these situations appear to be identical, okay? And this is at the heart of the equivalence principle, that gravity seems to be identical to acceleration. So let's continue with this Gedanken experiment. Let's suppose now this person in the accelerating rocket shoots up a beam from the left side of her room to the right side of her room. And as the laser beam travels the room, if we assume the acceleration is strong enough, well, during the time it takes to reach from one wall to another, the rocket is going to move upwards, and eventually the laser beam is going to hit on the right wall at the bottom of it. So essentially what the person inside the rocket should see, if of course the acceleration is strong enough, it's some kind of bending of light. This is what we expect from this very simple imaginary exercise. But if this is the case in our rocket, based on the equivalence we just established before, this should be the case also on the surface of Earth. All right? In other words, the gravitational field must bend light, just based on this reasoning. What's the problem? That Earth's gravity is, of course, too weak to observe this. And this is why this had never been seen before Einstein started making this kind of predictions. The gravity of the sun, however, a regular star like the sun, does a much better job, no? Because it's much more massive, so its gravity can be much more strong. And well, actually, it was a famous experiment, as probably most of you or all of you know, led by Eddington in the 1999 full eclipse that you could see in a couple of points on Earth, where they saw the curvature, the light bending around the sun of some stars. And essentially, this is what gave world famous, this is what made world famous Einstein, no? Worldwide. Let me make this note that light does not change the speed, okay? Here, what happens with the bending is that it changes direction, simply because it's following the trajectory dictated by the gravitational effect that we will describe in a different moment, in a different manner in a moment. So Einstein, with his great genius capabilities, understood in this manner, in these Gedanken experiments, that light should be bending in a gravitational field, that light should be red or blue shifting, depending of what direction is moving with respect to potential well, or gravitational potential well, that there should be time dilation and other effects. But he understood all of this just with this kind of experiment, without mathematics. So it became clear to him at some moment that, of course, he needed a mathematical formulation. Okay, and this is maybe what delayed the development of general relativity a few more years. So what is this formulation of general relativity? I'm going to try to be very brief, obviously, because we cannot dwell on a full lecture on general relativity here. So let us first consider the case of a special relativity. We consider an observer, a runner, that she's moving with constant velocity, and we draw her a space-time diagram. This corresponds to a straight line, which literally tells us that for a given finite amount of time, she will move a finite distance. However, if she happens to be moving accelerating, say using her own body power, the diagram becomes not a straight line, but a curve. No? And essentially what this acceleration tells us is that for the same amount of time, now she's capable of moving a larger distance. And this is why the trajectory is curved. So now remember that the identity we made before, that Einstein made before, is that acceleration and gravity should be equivalent. And now we are learning that if we want to draw a space-time diagram, this corresponds an accelerated motion to a curve, the space-time trajectory, this curve. And this is where the great genius of Einstein, reveals itself. No, it's a classical paradigmatic example of Einstein thinking out of the box. I don't really know what was the process in his mind, no, but he reaches or proposes the hypothesis that maybe gravity is actually the curvature itself of a space-time, if you think of a space-time as a manifold. No? So the famous theory of general relativity of Einstein would tell us in summary, like in a school presentation, is that matter curves a space-time. This is represented by this net here, by this curved lattice here, and matter is represented by Earth. And as there is a geometry of this represented by the curvature of a space-time, then motion of objects like a satellite will move around that curvature. Okay, that's the summary of what general relativity is in plain words. Okay. Now, let's go to write some useful equations. Let's go back to the situation yet where some observer is capable of hitting a baseball with constant velocity. This is of course not possible in reality in a surface of Earth because there is friction. But forget about friction, abstract yourself, imagine there is no friction, and it sends the ball with constant velocity. So he sees again a straight line, space-time diagram. Now another observer is moving with constant velocity with respect to the first observer, and she will also see a straight line as a space-time diagram, but we know from special relativity that their space intervals and time intervals are not equivalent. It's actually Lorentz transformation that connects them, and if you do Lorentz transformation, what we learn is that actually it's the space-time interval itself that is invariant. Okay? Sorry, 1 second. Let me put off the phone. I'm sorry. All right. So now, if this is what is invariant, maybe we can write it at the infinitesimal manner in this way, where here we have the time interval, here the space interval. We can swap the sign here. It doesn't matter where you put the sign, it's a choice. And to be more compact, we can write this with a matrix and vector notations, where now we are summing over repeated indexes. and where we are defining the metric tensor that corresponds to flat space-time, to special relativity, which is known as the Minkowski metric, okay, which I assume all of you are familiar with. Now, general relativity, in a sense, generalizes this and now changes the space-time metric, instead of by a static quantity, by a local dependent quantity, which describes the local curvature of a space-time manifold. But still, the space-time interval is invariant under this manner, from which immediately I deduce that given this invariance, I know how the metric tensors transform under general change of coordinates. Okay? So that's an important rule, actually, when you want to work with gravitational waves. So general relativity is like a generalization of a special relativity. And from the equivalence principle that we described with words before, at the end of the day, you can make a more mathematical formulation and describe what is the motion of a test particle, let it be massive or massless, in the curvature of a space-time manifold, where this curvature is described here by the Christopher symbol that contains the information on the metric. All right. And of course, if this is a flat space-time, this is 0, there's no curvature, and then this corresponds to rectilinear constant velocity motion. And the principle of relativity is generalized in general relativity to the invariance under general coordinate transformation, which tell us how the metric tensors transform. And after some work, okay, this is non-trivial, you end writing a consistent set of equations that tell us how space-time geometry, through this tensor that I will define in a moment, is curved, or is governed, is dictated by the presence of matter through the energy momentum tensor of this matter. Okay, and these are the famous field equations of Einstein. So let's put here the equations of Einstein again to highlight them. This is the Ricci tensor R mu nu, and this is the Einstein tensor G mu nu. Okay, and this is the energy momentum tensor. The coupling constant is the reduced Planck mass. And if we were to write explicitly the Ricci tensor, this is a combination of derivatives of the Christopher symbols and a bilinear combination of these symbols, where, remember, these symbols are bilinear combination themselves of the metric. Now, you see this theory is very complicated. That's the problem, because general relativity, at the end of the day, can be summarized as a theory that is nonlinear and that governs the dynamics of the metric through a second-order nonlinear differential operator, that is the Einstein tensor, over the metric, and sourced by the energy momentum tensor, sourced by whatever matter components in the universe. So essentially, to solve this theory, due to the nonlinearity of its own nature, it's very difficult, and this is why it took so long in the 20th century to develop some of the solutions and some of the applications. With this, I end the digression on general relativity. I hope that was good enough for those who may have not taken a course on general relativity or not interiorized so much general relativity yet. But in any case, by introducing those tools, we're going to use them now for gravitational waves. So I think we are in position to continue with the primer on gravitational waves. Yes. So now, summarizing and repeating myself for the sake of clarity, we are going to assume general relativity as a metric theory. It's a nonlinear theory which connects the geometry of space-time through the Einstein tensor to the energy momentum tensor of whatever matter in the universe. All type of matter, massless, massive, with special properties, charged or not charged, etc. All matter gravitates. Okay, it's a universal interaction. That's very important. We are going to exploit relevant aspects such that the theory of gravity, of general relativity, is invariant under diffeomorphisms, which is general coordinate transformations. And this implies, for instance, that the space-time interval written in this infinitesimal manner is invariant. What else? So if this is our framework, we have to work with this framework in order to define gravitational waves. So essentially, what could be, since this is a nonlinear second order, differential operator, how can we proceed? How can we proceed in order to define, anything that could resemble to a wave? Ideas, question to the audience, please. Maybe you can unmute if somebody raises their hand.
Yeah, please raise your hands and I can unmute you.
Yes, I repeat the question. No? Since this is a nonlinear second order theory, however, the concept of waves is a linear phenomena, what can we do to define something as a wave here? Any ideas?
Please raise your hands.
While you think, I have a sip of my coffee, so no worries. There is some comments in the chat. I don't know if they are referring to something. Mm-hmm.
Yes, someone answered your question, Danny.
Yeah.
Okay, look for small perturbations. Yeah, that's exactly correct. Okay, why is that? Because in order to define gravitational waves, and by waves, I remark that typically the phenomenal waves is linear. The only and first idea we can try, okay, because later on one can complicate things, but is to think of the metric as an object that is going to be, let's say this is the general metric, and it's going to be decomposed into a background metric that describes the background dynamics of whatever situation, plus a perturbation, a small perturbation on top of this background. So the idea is going to be that if I can do this decomposition, I plug it here into my nonlinear equation, and I try to linearize it. I try to find what is the equivalence to a linear equation over this perturbation. And in doing so, hopefully, I will identify what is within this energy momentum tensor, the particular part of it, the particular part of the energy momentum tensor that actually sources gravitational waves. Because since now I'm going to do a perturbation, it means that there's going to be a part sourcing the background, another part sourcing the perturbation. So our approach is to do perturbation theory, and this is done in so many branches of physics, with the difficulty that now we deal with a nonlinear theory, that of general relativity, and this becomes a bit cumbersome. So, as I was saying, we're going to take the approach of perturbation theory. And I hope you had yourselves a good doses of coffee, because you are going to need it to follow all of this. So I'm going to give various definitions of gravitational waves. Let's start by a first approach, first definition of gravitational waves, which is the one you typically find in textbooks, and the one that probably those of you who may have taken a course on gravitational waves probably has learned. It's not the one I like the most at all, but it's kind of pedagogical to start with, so let's take this path. So in our first approach of definition of gravitational waves, we are going to consider not a general metric, but a metric, space-time metric that can be decomposed into a Minkowski background and a perturbation on top of such background. Okay, since Minkowski amplitude entries in the matrix are order 1, plus or minus 1, what we are going to demand is that this the amplitude of this perturbation, absolute value, is much smaller than 1. So that is really a perturbation on top of the Minkowski metric. Okay. Now, if I demand this in general, what I'm doing, well, sorry, this approach in adding perturbation on top of Minkowski is called linearized gravity, obviously. Now, if I'm demanding that when I have a perturbation is on top of Minkowski, what I'm doing somehow is fixing the frame. What do I mean by this? Well, remember that the underlying symmetry that is the symmetry that defines general relativity is the diffeomorphism invariance, which is the invariance under general coordinate transformation. But if I'm fixing Minkowski in the background, how can I preserve Minkowski under a general transformation in the background? It's not possible, which really means that what I'm doing here is I'm breaking the full generality of general transformations. It's like, instead of taking the full arbitrary general transformation, if I want to fix this frame, I have to break that and content myself, okay, and remain happy, sufficiently happy with the fact that maybe we can take a subset of this general transformation. We can pretend to make them general as possible within a certain restriction. They are going to be infinitesimal transformations. Those are the only ones we can tolerate. So they are general, because they are infinitesimal because I add up some vector here on top of my coordinates, that's the transformation, and they are general, but because this is an arbitrary function, okay? But they are only a residual symmetry, if you want, of the original full general transformation. And since what I want is that my metric always remains in a Minkowski background plus a perturbation, this immediately tells me how these perturbations transform. They transform like this. The new perturbation is equal to the old one plus a linear combination of derivatives of this object here, which means these derivatives must be smaller or of the order at maximum of the perturbation, the original perturbation itself. Because otherwise, if this becomes bigger than 1, then you are not in a background of Minkowski anymore with a perturbation. Okay. So I hope this is understood. So by demanding this approach in which we assume background of a space-time is Minkowski, which is a good approximation in many situations, obviously here on Earth, for instance. No? We are locally living a Minkowski background plus some perturbation, but certainly not everywhere, not in the universe, for instance. So by assuming this, we are fixing the background frame somehow. We still allow for change of frames under a residual symmetry, which is an infinitesimal general diffeomorphism transformation described by this rule here. And as long as the derivative of these guys are not large, so they are smaller than the original perturbation, we are fine. We will maintain this form of our decomposition. Now, this serves me to introduce some notation. So what is this notation? Whenever I write derivatives of a vector object with indexes with these parentheses like this means I'm symmetrizing over these indexes. Whenever I write derivatives or other differential operation with square brackets like this, it means I'm anti-symmetrizing the indexes. Okay, this is kind of important because we will use this notation a bit more later on. Try to keep it in mind, please, if possible. So, well, we've understood that it is possible within the framework of general relativity to make not a general transformation, but an infinitesimal one, and still preserve this decomposition of a perturbation, a small perturbation on top of Minkowski background. Good. Let's introduce this decomposition now into Einstein equations. First, before doing that, we define, because it's clever to do so, the so-called trace reverse metric perturbation, which we identify with a bar here. And that is the same perturbation as before, minus 1/2 the trace of that perturbation times the Minkowski background. Okay. Now, if we define this, we defined it, if you want, for convenience, because the expansion of the Einstein tensor at linear order, okay, we are neglecting second order effects, so we are only expanding to first order. It actually has this very simple manner, relatively simple, in terms of this trace reverse metric perturbation. Of course, here, everywhere it says h bar, I could plug in this form, and then I would recover the full expression of the Einstein tensor expanded to first order on top of Minkowski in terms of the original perturbation. I think it's more practical to do it with this trace reverse thing. It is an exercise you could do to find this form at linear order. It's not a difficult exercise, but one needs to be familiarized with general relativity and with tensorial calculus pretty much in order to do it in an efficient manner. I think in the homework, I prepared some exercises that I put in the Slack channel already. Not sure if I really give you the steps to derive this first step, but I certainly give you others to derive eventually a wave equation for gravitational waves. But anyway, you will look into those exercises in another moment. Now let's focus here. We have this expansion to first order, very good. And now remember, because this is a general decomposition, that we have a residual symmetry, which is the infinitesimal diffeomorphisms, right? So why not to apply it? Let's consider that we have this situation. We are in a given frame where we have Minkowski and a given perturbation. And this perturbation, we don't know what it is, but we make a change of coordinates in this infinitesimal manner. Remember, this implies that the derivative of this displacement vector must be small. And then we demand that the new trace reverse perturbation is 0. So how do I do this in practice? If a priori, let's say, the original perturbation, its derivative was non-zero. Let's imagine I give you this, you take derivatives of the trace reverse version of this, and it turns out that this is non-zero. But you want to impose it to be 0 through your infinitesimal transformation. Well, let's do the transformation. I transform here the coordinates, and I transform here the tensor. I am noticing a typo here. Sorry, this should be circular normal parentheses, not a square bracket. Sorry about that. Well, so look at it. If this guy, its divergence originally is non-zero, let's call it F, this means that the divergence of the new perturbation of this one, the one I call H prime, it's equal to the previous divergence, non-vanishing, minus box operator in Minkowski of this vector displacement vector. Which means that if I want to make 0, this guy on the left-hand side, all I need to do is to make 0 this equation and solve for the equation of box wave equation over psi equal to whatever this function we obtain here. Okay, for each index nu, there should be an index nu here. And this solution, this is the wave equation. This is the wave equation. It always has a solution, okay, given f of x with index nu. So, in other words, if originally the divergence of my perturbation was not divergenceless, this is what this Lorentz gauge condition means, I find what are the coordinates psi that I add into my previous coordinates, such that now in my new coordinates, x prime, the condition of Lorentz gauge is fulfilled. I hope this is clear. So once I am in this frame with this new set of coordinates, here in this frame of coordinates, my perturbations are divergentless. In particular, the trace reverse perturbations. Very good. This has a beautiful implication that the expansion, sorry, what direction am I going? Yeah, the expansion we had before of the Einstein tensor that had 3 terms, it turns out that 2 of them are vanishing directly in this gauge, just because they are involving derivatives of the indexes, contracting indexes from the tensor perturbation and the derivatives, precisely what the Lorentz gauge vanishing condition is. So these 2 terms vanish actually in this new gauge where we are. We can eliminate them, and we can simply equate the left-hand side left by this wave operator over the trace reverse metric equal to the energy momentum tensor of whatever matter content of the situation. Very good, no? So we are already progressing, no? Because not only we have now a linearized version theory of general relativity, this is looking more and more as a wave, no? Because certainly this is the wave operator in Minkowski. Now, notice that originally H mu nu, it's a 4 times 4 tensor, symmetric. And because it's symmetric, instead of having 16 independent entries, it has 10 independent entries, just the upper triangular part of the matrix and the diagonal part of the matrix. Whereas the lower triangular part, it's identical to the upper one from a symmetry of this tensor. Now, because we demand these 4 conditions, because Lorentz gauge are 4 conditions, you are contracting nu with itself, but you have 4 in values for the index mu free. So these are 4 conditions. Now you remove 4 degrees of freedom out of the 10 from these 4 conditions. So this equation, what is describing is 6 degrees of freedom, governed by this kind of wave equation, which is only valid, of course, in the Lorentz gauge, only when you are in that gauge. Is that all? Is that all about gravitational waves? I have arrived to a gravitational wave equation over gravitational metric perturbations. I know there are 6 degrees of freedom here because I'm subtracting 4 out of the original 10. Yeah, what do you think? In this case, I'm going to answer myself. Probably you know the answer. Not at all, because everybody knows that the degrees of freedom of gravity, they are 2, not 6. No. So what's going on? What's going on? Well, what's going on is that we haven't saturated our residual symmetry. Okay, remember that our residual symmetry allows us to change from one system of coordinates to another through infinitesimal deformation of these coordinates. And in order to preserve the Lorentz gauge, what I can do now is to change into a new Lorentz gauge frame where I demand that the Laplacian, the flat Laplacian of this vector is 0, is vanishing. And this is absolutely compatible with what we were doing before. If this guy was 0, then all I need to do is that the box operator over the new displaced vector is equal to 0. And that's precisely what I'm doing here. So I'm exploiting the fact that I still had this further residual gauge symmetry, which allows me to move from one gauge, Lorentz gauge frame to another Lorentz gauge frame. Yes? And why is this relevant? Because now I can move into a new Lorentz gauge frame where you see, I'm preserving the Lorentz gauge condition, but why is this relevant? Because I can go to a system of reference where, in the absence of the source, okay, for the moment, let me consider that situation, so very outside the source, I can make explicitly 0 certain components through this transformation. I make 0 any element involving the 0 temporal component. I make 0 the trace, and then the Lorentz gauge condition actually just becomes the divergence-less of this spatial tensor, this 3-dimensional tensor. Okay, and this is called the transverse traceless gauge. But notice that at this point, as we are doing things, this is a gauge choice. That is, we are choosing a very special system of coordinates, which we call the transverse traceless gauge system of coordinates, where this is true, manifestly true. And these are Lorentz gauge system of coordinates that we have chosen especially such that we can make explicitly 0 these guys here. And why is that relevant? Because now, if you realize, well, in the absence of the source, we can still write the previous equation, a wave equation over these Hij guys. But now, because before we had 6 degrees of freedom, and this further residual gauge condition corresponds to 4 conditions, as many as components of this displacement vector, I can remove 4 degrees of freedom out of the original 6. This is why I'm allowed to do all of this. And out of this 3 times 3 matrix, where there should be 6 degrees of freedom, actually I remove 4 degrees of freedom from these constraint conditions, which are 4, and I'm left with 2 degrees of freedom, which is what everybody knows. Okay, I hope you are following the logic. So we are left with 2 degrees of freedom propagating in this special system of coordinates, the transverse traceless gauge. Now, what happens if I am not outside, very far away from the source? I'm actually very close to the source, or even inside the source if it's a continuous medium. Can I still take the transverse traceless gauge, which amounts to take to 0 these components? I'm not sure I dare to ask this to the audience. Yeah, let me ask. Okay, let me ask quickly. Anybody has an answer to this? Can we take the transverse traceless gauge in the presence of the source? Yes or no? If somebody knows, we take the answer. Otherwise, I try to answer myself. We wait a few seconds if there is someone brave to answer.
Please raise your hand if you have an answer.
Okay, there is something in the chat. No, we can. One person says yes, we can take the transverse traceless component of T. No, we cannot take. Okay, the first person is anticipating an answer that we are gonna deal with later on. The second and third person are given the correct answer, but I'm gonna justify. So it is not possible actually to take the transverse traceless gauge, because since this implies to take vanishing these components, you cannot apply this, for instance, to the energy momentum tensor, which has to be equal here to these vanishing components. So there is no reason why my source should have the 0 elements or vanishing, or to be traceless. No reason whatsoever to imply that over the source, over the general energy momentum tensor. So it's not possible in general to take the transverse traceless gauge in the presence of a source, but this doesn't change the fact that there are still only 2 radiative degrees of freedom. It's simply that I cannot make manifest in a gauge explicitly, when there is a matter, the transverse traceless gauge by making 0 these components, because this would be incorrect balancing the non-zero components of the energy momentum tensor. Okay. Now, as another person was anticipating in the chat, we will see that there is a solution to this issue, but that will come in the next approach to define gravitational waves. So, summary: first approach to define gravitational waves in the transverse traceless gauge, which is a very special choice of coordinates. We are left with 2 degrees of freedom, which essentially are encoded inside this 3×3 matrix. And as long as we are outside the source, we can really take this gauge, make explicitly 0 these components. And then we know that the general relativity equation boils down to this wave equation over this transverse and traceless degrees of freedom. And this is why we actually speak in first place of gravitational waves, because the linearized version of the Einstein equations actually becomes itself a wave equation, a wave operator, at least in this Minkowski background approach. Can we gauge away now these gravitational waves? Well, the answer is no, because we have saturated now our capability of making gauge transformations of the metric components. There is no further freedom once you go into this gauge to remove further any degrees of freedom. At most, you could introduce any new functions that were not vanishing, again not vanishing, which doesn't mean you have more degrees of freedom. It simply means that you don't see explicitly these 2 degrees of freedom in this transparent manner. That's all it means. It's not possible to gauge away these degrees of freedom here, remaining 2 degrees of freedom we have. So how does it look? A gravitational wave in this gauge, in the transverse traceless gauge? Well, we know it's transverse, so whatever the effects of the distortion of Minkowski have to be transverse to the direction of propagation. This is what this condition determines. And secondly, we know it's traceless. So we know that in this transverse plane, whatever the perturbations, they have to be traceless. Hence, we know there are 2 polarizations in total, or 2 degrees of freedom. We can write in a general manner a matrix in the two-dimensional plane transverse to the direction of propagation, okay, in this plane, where A, B are only the coordinates in this transverse plane. We can write it as a superposition of plane waves, because this is a wave equation and the general solution is a plane wave. And the tensor here in that transverse plane, it can be decomposed in a unique manner, if you want, in 2 degrees of freedom. And since we have to write a matrix that has only 2 degrees of freedom in the transverse plane, represented here by the X and Y directions, and since it has to be traceless, then the first degrees of freedom has to go with opposite sign in these 2 entries, in the diagonal entries. And hence, since it has to be symmetric, the second degree of freedom has to be this other function here. So you see, we are forced to write naturally, just following the logic that there are only 2 degrees of freedom, in this form, any gravitational wave that is propagating in the z direction, where z is an arbitrary n direction, of course. Yeah. What is the effect of these 2 modes? These are called the plus and cross polarizations. Well, if you happen to have a set of a ring of test masses that are just floating magically in space, and then you get one of these H plus wave going transverse to it, what the plus mode does is to squish the ring in this way, then goes to normal manner, then squishes the ring in the opposite direction, then goes back to original position, then squeeze back in the former position, and so on and so forth. This is why it's called plus, because as time goes by, it describes like a plus. And the cross term, it does something very similar, but in the diagonal direction. In the diagonal direction, we respect this chosen imaginary system of coordinates x, y in the x-plane, and z going transverse. And if you want to see beautiful videos of how the passing of gravitational waves through this system of test masses really look like, you can notice that in my presentation there are a couple of YouTube videos here. You can click there and see yourself the videos. So definition of gravitational wave second approach, but first of all, are there any questions about this first approach?
Please raise your hand if you have any questions. Okay. Please unmute yourself and speak. Sataj. Yeah, go ahead.
Hello, am I audible?
Hello.
Hi, Daniel. So my question is from the first slide where you have defined your h mu nu is very, very less than 1, right?
Yes.
So because if you take eta mu nu absolute value, so the diagonal is 1. Diagonal is 1, 1, 1. Okay. So for the diagonal, I can understand that h mu nu, the matrix h mu nu should be less than 1. But for non-diagonal, I have a problem to understand it. Can you please elaborate it?
Yeah, no, you are absolutely right. In that case, the meaning of perturbation is not very well defined, because if you have off-diagonal terms, of course, whatever as small as they are compared to 1, they are infinitely larger than 0, no? Like in the Minkowski background. But it's a technicality. Yes. We just allow for it, you know, because at the end, all we care is that in the diagonal they are much smaller than 1. And then for consistency, because it doesn't make sense to think of a perturbation that is completely perturbed in the diagonal and not in the off diagonal, we put everywhere in the matrix of diagonal and in diagonal smaller than 1. But you are right. If we go strict with the meaning of perturbation, in reality, what we are saying is that there is -1 plus a perturbation, +1 plus a perturbation in the diagonal, and then some non-vanishing value over 0. Yeah. But there is no conflict with it, you know, because at the end of the day, the whole point of this is that you linearize your Einstein tensor into the amplitude of these new tensors, which have all the components. Okay, so there is no contradiction or there is no problem whatsoever with it. Thanks for the question.
Okay, so may I ask one more question?
I'm happy to go for it.
Okay, so like you have said that H mu nu has 10 independent component and 4 of them will be gone due to the infinitesimal coordinate transformation and 4 of them will be gone due to the residual gauge, right?
Yes.
So suppose if we have massive graviton theory, so this is 2s plus 1, so s equal to 2, so it should be 5 independent component, right?
Yes.
So
That's not general relativity. In the moment you put that
yes.
mass, yeah, that's not general relativity. Yeah, that's why you have more degrees of freedom. That's right.
Yes. Okay.
You cannot
Okay.
do this whole game that I'm doing here. Yeah.
Okay. Thank you.
Yeah, that's it. Yeah, yeah. If you include a mass for the graviton, it's very simple because you see in everything I've done, as you see, the equation I was left with was a wave equation with no mass term. Okay, and this is why you have 2 degrees of freedom. Otherwise, you have 5, as you are saying. But that wouldn't be general relativity. Yeah. Okay, any other question?
I can't see any, Danny.
Okay, then I'm very happy to. There's another question.
Oh, there is another question. Just
Let's take one more and then we
Yeah.
continue and finish the lecture.
Leiden, unmute yourself and speak. Yeah.
Hello, Professor.
Hello.
My question was, so we said inside a source, I mean, we can't use the transfer stressless gauge, but inside a source, can we still write the metric as Minkowski plus a small perturbation in the first place?
Yes, yes, you can do that. That's consistent because look, the source here is suppressed by the Planck mass, which is very large. So only if you had super Planckian energy densities, you know, or components of this energy momentum tensor, then you would spoil the fact that this is a perturbation. And typically you don't have that, obviously, in normal field theory or standard situations at all. Actually, that would require a more complicated theory because all of this would not be valid. So there is no problem to be within the source. And actually, we will see this in the next approach, okay, where we can in full generality include a source. And this can be very large, and still you have a perturbation over the background metric. And thanks to the weakness of gravity, yeah, which is manifested through this Planck mass suppression here. Clear? Okay, I hope so. Okay, thank you very much, guys, for the questions. We can, of course, have more questions at the end of the lecture. Let me go for second definition of gravitational waves, which second approach, which I definitely like much more myself. Because the other approach gives the impression that you need to go into a gauge, which means you need to go into a special system of coordinates. And of course, the nature and existence itself of gravitational waves cannot be related to what system of coordinates you are, right? That already smells bad. So let's see what can we do in order to stop ourselves from having to define that special system of coordinates. Second approach, it's called the gauge invariant definition of gravitational waves. We are gonna be still modest people and remain within the approach that we are going to perturb only or add perturbations on top of Minkowski. Again, much smaller than 1, in order to be consistent with having perturbations at least in the diagonal, but yet the background is going to be Minkowski. Later on in the third approach, we will take a general background, a space-time fully dependent background. Now, we are going to do a very nice trick, which is that due to the symmetry of the background, Minkowski, which is, you know, homogeneous isotropic, we can decompose actually the metric perturbations into so-called scalar, vector, and tensor parts. And I'm sure you've seen this already in the lectures of David Wons. I believe David is doing that in a cosmological framework. I could, of course, do that here, but I think it would make a bit less transparent the whole point I want to emphasize here. So I rather want you to focus on this simplified situation where we are in Minkowski plus perturbation. But in reality, what David probably is doing in his lecture is he's decomposing perturbations on top of Freeman-Lemaitre-Robertson-Walker, which is conformally connected to Minkowski. Okay, because for flat space-time, you just put a scale factor here, essentially. Anyways, forgetting about the expansion of the universe, focusing on this case, the decomposition is the same. As long as the background metric has this has isotropy property, actually this is the relevant one, we can decompose our perturbations into scalar, vector, and tensor, which we will see in a moment what I really mean by this. You already see the form here. Now we will discuss further what this form really is. And I can do the same, because nothing prevents me from not doing it, to decompose also the energy momentum tensor, like this, like a scalar, some vector components, some tensor components. A scalar vector tensor decomposition. Okay, so I do that with the metric, a space-time metric. I do that with the energy momentum tensor, which means that now I'm splitting the degrees of freedom of both of these guys, both of these tensors, into scalars, so pure functions. For instance, for the metric, here I identify 4 scalars. One defining the 0, 0 component, another one of which I take a gradient characterizing one part of the 0i component, another one of which we just multiply by the delta Kronecker characterizing the ij metric component, perturbation, another one of which I take derivatives, again characterizing another part of the ij tensor perturbation. And the same goes for the energy momentum tensor. Okay, I identify one scalar component for the 0, 0, another one for the 0i, and 2 for the ij. There are also vector components. So here I have a pure vector directly, the 0i metric perturbation, and here I take gradients of this vector in a symmetric manner in order to define this symmetric perturbation. And again, you can do absolutely the same decomposition with vectors in the energy momentum tensor. And finally, I can take a pure tensor, which is just one function here and another function here. I hope this is clear. Altogether, if I were to consider these scalar vectors and tensors in a 3-dimensional, in this case, Euclidean space, because Minkowski, the spatial part, is Euclidean space. So if I were to consider all degrees of freedom encoded in 4 scalars, 2 vectors, and 1 tensor of 3 times 3 components, this would be 1, 2, 3, 4. Each of these would have 3 components, no, a 3-dimensional vector, so 6. And 4, 10, and this would have 6 independent degrees of freedom in a symmetric 3 times 3 matrix. So apparently I have 16 degrees of freedom. But we know immediately from the symmetry of the metric tensor or the energy momentum tensor that there should be only 10 degrees of freedom, at least to start with. And in order not to overcount, in this decomposition, to make it mathematically consistent, it's necessary that we take some constraints. So all vectors are divergenceless. And if you take a vector of 3 components, but you say it must be divergenceless, this represents one constraint, so you remove one component as an independent component of the vector. So each vector in reality, it's only having 2 independent components. And the tensors, like the hij here, if I make them divergenceless, this implies 3 constraints because there are 3 values of the free index. And if I make them traceless, this implies another constraint. So in total, I have 1, 1, 1, 3, plus another 3, 6 constraints. So it is clear that in reality, I can do the same, of course, in the energy momentum tensor, divergenceless vectors, transverse and traceless tensors. So in reality, I have 6 constraints for each tensor, which means that I don't have 16 degrees of freedom, even if they look like a priori, I actually only have 10 degrees of freedom. Good. Now, we know that physically there cannot be 10 degrees of freedom because we already did an exercise in a special gauge where we saw there are only 2 degrees of freedom at the end of it. So how do we get there? Well, let's apply physics. First physical constraint. Energy momentum tensor is conserved. Since I'm in Minkowski, I take normal derivatives, not covariant derivatives. This implies 4 conditions, right? Because there is one free index, nu, here, which takes 4 values. And these 4 conditions give me 4 relations, actually. one constraint relating scalar modes of the energy momentum tensor, another constraint relating, again, scalar modes, and one relation between the vectors that corresponds to two constraints. So there are 4 constraints due to energy momentum conservation, which means that at least for the energy momentum tensor, out of the 10 degrees of freedom, I remove the 4 constraints, I only have 6 degrees of freedom. Okay, that really resembles more what we already knew from before. What about the tensor, the metric tensor? Well, the physical constraint like this over the energy momentum tensor applies actually over the Einstein tensor, not the metric tensor. So I could only do the same exercise with the Einstein tensor as I did with the energy momentum tensor, but that would complicate how to relate the metric tensor degrees of freedom. So instead, what I do is I exploit the physical symmetry that I still have underlined. Remember, infinitesimal transformation such that the vector here, the displacement vector, changes the metric perturbation only in this manner, through this symmetric combination of derivatives. I can do that. And now let me decompose the displacement vector into this manner, such that I define a scalar degree of freedom for the 0 component, another scalar degree of freedom of which I take the gradient to define part of the vector part of the spatial part, and another pure vector of which I demand it is divergenceless. So in total, I have 4 degrees of freedom, 2 scalars and 1 pure vector, 4 spurious degrees of freedom, which I can gauge away if you want by making this transformation. I make it, and this is how all the, just following the rule, how all the scalar, vector, and tensor perturbations transform under a general infinitesimal coordinate transformation. This is a standard rule. I'm sure you've seen it if you've studied cosmological perturbation theory. Probably David has written something similar like this. If not, okay, this is the version for Minkowski transformation as a background, okay, when Minkowski is the background. And very relevant to note is that the vectors change, the scalars change, but the tensors do not. So the tensors are already gauge invariant. But okay, first of all, because here we have 4 guys here encoded in this new scalar and pure vector, I can remove again 4 degrees of freedom and be left with 6 degrees of freedom in the metric tensor. And now, because I have this general rule of transformation, what I can think of is of making gauge invariant quantities. Just thinking a little bit, okay, this is what actually Bardeen did in the early 80s for the cosmological setup, but as I said, it's pretty much the same here. And then you can think of how to exploit this transformation of this symmetry and produce these, for instance, scalars that are gauge invariant. So these scalars are gauge invariant. They are formed by various of the original scalars. When you transform them according to these rules, the one on the left-hand side is always invariant. The same goes for this one. And I can also make a divergenceless vector that is actually gauge invariant by linear combination of the 2 vectors I already have. So here I have 2 degrees of freedom, 2 scalars, 2 degrees of freedom in the divergenceless vector, and 2 degrees of freedom directly in the directly gauge invariant tensor HIA. In total, 1, 1, 2, 2, 6, as expected. But now I wrote everything in terms of gauge invariant quantities. And this is beautiful, no? Because this is what physics is about. You don't want your physics to depend about your choice of a system of coordinates. Of course not. What you want is that the physics is invariant, is independent of your choice of coordinates, obviously. Now, if I can write perturbations which are gauge invariants, it means that I can write my Einstein tensor in terms of these gauge invariant perturbations. And of course, this is a very nice exercise that if you want to do once in your life, I believe this is a great achievement to do this as a theoretical physicist, because it's a non-trivial observation to realize that you can really write the Einstein tensor as a function of the gauge invariant infinitesimal under gauge invariant infinitesimal transformation in terms of this scalar vector and pure tensor. Why is this relevant? Because then I can write equating this Einstein tensor to the energy momentum tensor I can write in a gauge invariant fashion the perturbed Einstein equations. If this is not amazing to you, sorry, let me highlight it again. I am writing in a gauge invariant manner the perturbed Einstein equations. So these equations, as long as I'm in the situation where I have a general small perturbation over Minkowski, they do not depend on the gauge choice. They are gauge independent. And this is what's gonna help us now to identify what is the true nature of the gravitational waves. As you notice, all perturbations, scalars and vectors, they are Laplacian equations. They are not dynamical equations. The only one that has propagation that is dynamical because it mixes time and space derivatives is the pure tensor mode, sourced by the pure tensor part of the energy momentum tensor. And now what we are learning here is that in reality, the transverse traceless degrees of freedom of your metric perturbations and of your source are what really create and propagate gravitational waves. And this has nothing to do with the gauge choice. What happened in the first approach is that we move ourselves into a choice of coordinates where it became manifest that the only perturbations remaining were the pure tensors. But that doesn't mean that if I go to another gauge, another system of coordinates, always through infinitesimal transformations, please remember, that doesn't mean that the gravitational waves are different than the transverse traceless degrees of freedom. We simply had to do this exercise to realize. So now what we are learning here is that independently of the gauge choice, only the transverse traceless degrees of freedom are propagating as a wave. And they are sourced by the transverse traceless part of the energy momentum tensor. Only radiative propagating wave degrees of freedom are gauge invariant actually. So it's fantastic because the whole formalism of the theory itself immediately identifies that the only gauge invariant degrees of freedom are those who actually propagate gravity, whereas the other ones are static quantities. Gravitational waves are therefore, and should be, identified, at least in the perturbative context, with the transverse traceless degrees of freedom of your metric, independently of the system of reference. Okay. Now I have third definition of gravitational waves, the most general one, but I realize it's like 1:30 for me, which is probably about the time I should finish.
Yes.
So I'm gonna skip this. It's okay because we can cover it tomorrow at the beginning of the next lecture. No worries. So just to summarize, we have covered linearized gravity in Minkowski, but forcing ourselves to go to very special gauge choice. We have learned with a second approach that by decomposing perturbation into a scalar vector tensor, actually the tensor perturbations are the ones to be fully and really identified with gravitational waves. And we will learn tomorrow that in general backgrounds we can do something similar. To finish the lecture, some perspective. Once we have identified that gravitational waves are transverse traceless degrees of freedom, now we can repeat the exercise, I will not do it in detail, to derive what is the equation of motion in the curved space-time of the universe, Friedmann, Lemaitre, Robertson, Walker. And this is essentially the same perturbation I was considering over Minkowski, except that now we have a conformal factor, the scale factor, okay, in conformal time. So if you linearize Einstein equations, again, you have a wave equation over these transverse traceless degrees of freedom, now with a friction term, because we are in an expanding background, and it's sourced by the transverse traceless degrees of freedom of the anisotropic stress, which is any deviation of your perfect fluid energy momentum tensor of the background. So the whole point of the lectures, next two lectures, is to look into situations of the early universe where at the fundamental level we can identify scalar fields or gauge fields or fermions, all of which develop a non-trivial transverse traceless part, which we know is a source of gravitational waves. Okay? So we will look in the next two lectures, after we define the third approach of gravitational waves, for what situations in the early universe create source naturally gravitational waves. To be continued tomorrow. Sorry, I'm 1 minute late.
No issues.
Thanks a lot, Danny. Wonderful, for a wonderful pedagogical lecture.
Thank you, Robert. Thank you, everyone. If there are further questions, if the students have a small break, I'm happy to take them right now.
Can you raise your hand if you have questions? Can you raise your hands if you have any questions?
I hope it was not very intense. You know, I get carried away sometimes.
There's a very positive comment in the chat.
Okay. Okay. Thank you very much, Priyanka. I hope I pronounced more or less your name.
Okay. If there are no more questions, thank you, Danny.
My pleasure.
We'll see you all tomorrow.